And I recommend you watch both because the easy way is easy to think about, but you will actually need to know all the meiotic stuff and things like that when you get to later chapters in your handbook. Okay? So we're going to look at the easy way to do the dihybrid cross, right? So now we have two genes. So I have the genes we looked at before, the H plus gene, which gives you curly hair, the HS gene, which is recessive and gives you straight hair, and then I have the wild type brown-eyed gene, so E is for eyes, and then I have the E recessive blue gene, so E superscript B, right? And we're going to skip over the whole parental thing, just assume both of them were true breeding for whatever traits they had, right? And they created some heterozygotes. So we have heterozygous H plus HS for the hair gene, right? And then we have heterozygous E plus and then EB for the eye gene. So you have one gene for brown eyes, one gene for blue eyes. And what we're trying to figure out in the end, right, is what fraction of the offspring are dominant for both eyes and hair, are recessive for the hair and then dominant for the eyes, are dominant for the hair and recessive for eyes, and then are recessive for hair and recessive for eyes. So what we're going to do is treat these both as individual monohybrid crosses, and then we're going to use all the things we know about probability in order to combine these, because you notice I use the AND clause there, woohoo! So that means we multiply, multiplication rule. Okay, so we're going to pretend that we're just looking at the hair gene, right? So we're going to treat this like we're doing a monohybrid cross of two heterozygotes for the hair gene. And we know what the Punnett square is going to do. It's going to give us a phenotypic ratio, because that's what we're looking at here. Whatever we can see is the phenotypic ratio of, we're going to get the phenotypic ratio of the offspring. So we know that 3/4 of the offspring, right, are going to be curly-haired. And then we know 1/4 of the offspring are going to be straight-haired. Okay, so we have our first trait, right? Our first probability. We know probability of curliness is 3/4, is 0.75. So now what we're going to do is the same thing for the eye gene. So we have two heterozygotes, right? And we know that we're going to get the same ratios. So 3/4 of the F2 generation that comes from the mating of two heterozygotes, right, are going to have the dominant color, the brown color, E+. They'll be E+, ES, and heterozygous, but showing the dominant trait, or E+, and be homozygous for the trait. Either one's fine, because it doesn't matter, all we're looking at the phenotype right now. But you could use this for the genotype if you wanted to figure out the genotypes as well. Okay, so what you're going to do is we're only going to look at the curly situation, because these are independent events, right? So it's not like you're going to be both, like being dominant for one makes you more likely to be dominant for both. You have the same probability. So you will have a 3/4 probability of having brown eyes, and then a 1/4 probability of having blue eyes. And then the same thing happens here, right? So since this is independent, we're going to do it again. We have a 1/4 of these, so we have 1/4 of the offspring already have straight hair, but then 3/4 of that 1/4 have brown eyes. And then 1/4 of that 1/4 will have blue eyes. So the probability of having curly hair and brown eyes is going to be 3/4 times 3/4, which is 9/16. Curls and brown. Then we'll have 3/4 times 1/4, which is 3/16. Curly, curls, and blue. We have 1/4 times 3/4, which would be 3/16 straight hair and brown eyes. And then the one that we would expect to be the least common, because it's double recessive, is 1/4 times 1/4 equals 1/16 straight hair and blue eyes. And then you can just plug these into here. So 9/16, or you could do, well, I have the fractions up here, so I'll write the ratios in here. So the ratio is 9 to 3 to 3 to 1. And you have to remember that because it will come up over and over and over again. So I just want to show you that you could do the exact same thing if you were interested in doing, in figuring out the number that would be, let's say, like homozygous for curly hair, homozygous dominant for curly hair, but then heterozygous for brown eyes. You can do exactly the same thing. So let me erase this, and you wouldn't even need to do out the whole tree. So I'll give you one last look. I'll pull it up real close. There we go. And now I'm going to erase it. On how to use probability trees is, now we're going to talk about what if we have like a more random question that you want to answer without doing out all the math, and you want to use my previous technique that I showed you for the easy dihybrid cross. So we have a dihybrid cross again. It's the same exact cross. You have two heterozygous for both genes, right? And so now we're looking at what is the probability that you get an offspring that is homozygous dominant for the straight hair, or for the curly hair, and then heterozygous, E plus EB, for the brown eyes. So they're heterozygous brown eyes. Well, so we know that the probability, right, when you cross H plus HS with H plus HS, the probability of this, so we can actually write this in probability H plus, right, is, this is a 0.5 chance, this is a 0.5 chance, equals 0.5 times 0.5, which equals 0.25, right? So you know that 1/4 of the offspring in the hair part of this cross is going to be H plus, H plus. Now we're going to do the same thing for E plus EB, right? So we want to know when we cross E plus EB, crossed with E plus EB, what is the probability that you get a heterozygous, E plus EB, like their parents? So we know that when you do out that Punnett square, right, you're going to get two of those squares that'll be heterozygous, right? So it's going to be like this square and this square are going to be heterozygous. So you have a 1/2 probability, or you have like, it's essentially like, the way you would do this out mathematically is 0.5 times 0.5 plus 0.5 times 0.5. So this would be 0.25 plus 0.25, which equals 0.5. That's the longhand way of doing it. So you know that you're going to get 1/2 of the individuals that are going to be E plus EB, right? So you can always do out, so then, you know, you essentially just multiply this, and then like you have E plus EB, which is 1/2, and you'll get like 1/8 of the individuals will be H plus, E plus EB. And you could even do this, like you could make another one and go like 1/4 of these are going to be E plus, 1/4 are going to be EB, EB. So then you would get the whole tree where you're like 1/4 times 1/4 is going to be equals 1/16 will be H plus, E plus, E plus. You can do all of these things, or you can do 1/4 times 1/4 will be H plus equals 1/16, which will be H plus, ES, ES. Okay, so that's a lot of math on one board. Let me bring it closer to you so you can just see all my crazy mathematics here. But the idea is you can use these probability trees for all sorts of things. So figure any sort of, if you ever need to quickly, without doing out the whole Punnett square and counting, like figure out how many individuals in a dihybrid cross are going to be heterozygous for both traits. You could do that very easily just by doing this doing the multiplication tree. And then if you're going to do the phenotype, you can do the same thing. So you can figure out, 3/4 of these individuals will be dominant, and dominant trait, another 3/4, so you know that dominant for both traits will be 9/16. So anyway, that is my fast and easy way of doing this, and I will post up a longer description of how the dihybrid cross works and why you get all these ratios from Mendelian genetics at a later date. But I thought I'd put these up right now really fast so that you guys would have the extra material.